So this is the second video out of two for a Couete flow being solved using the Navier Stokes equations. In the first part we derived an expression just here for the velocity profile at any distance from our moving plate, from our stationary plate to our moving plate. In the second video we will discuss the shear stress of the fluid acting on this plate. So I wrote here the shear stress equation for a two-dimensional flow, which in our case is two-dimensional for the Couete flow. Now I've also written down here the velocity profile we found. So this here requires the partial derivatives of the velocity profile. Now, as we mentioned in the last video, the flow is only flowing in the x1 direction with respect to x2. There's no vertical flow. So that means the partial derivative of u2 with respect to u1 is equal to 0. So if we differentiate our velocity profile, we get du1 by dx2 is equal to up over h. So plugging this into our shear stress equation, we get tau is equal to minus the dynamic viscosity times by up over h plus 0. So that's equal to minus dynamic viscosity times up over h. Now sometimes you may be given the dynamic viscosity in terms of the kinematic viscosity. So this mu here is also equal to viscosity times the density. So tau 1, 2 we can say is also equal to viscosity times rho up over h. So these, either one of these two equations are equally valid depending on what conditions you have.